We've been talking about gas laws, and we've talked about Boyle's law and Charles' law and Avogadro's law, and all of these related to of the parameters that define a gas. And so the ideal gas law brings all of these together into one law. And there's some nice math behind that and how we can combine all those, but we'll just kind of skip over that. And this is the guy right here that we're interested in. What color do I have going on here? Let's go with green today. So PV equals nRT. That is the ideal gas law. This relates the pressure, the volume, the number of moles, and the temperature of a gas. And there's a new letter in here, capital R. R is the universal gas constant. And it can be expressed in different units. The one that we're going to use, that we use most often in chemistry, is 0.08206. The units seem kind of weird there. Liter atmospheres per mole Kelvin. But let's just look at the units real quick. If we have our pressure in atmospheres, and we multiply that by the volume in liters, and say that that's equal to the number of moles, the units for, so atmospheres is the units for P, and volume has the units of L, number of moles has the unit of moles, R has the units liter atmospheres per mole Kelvin, and then what do we measure temperature in? Kelvins. So this is kelvins on the outside. Let's look at what happens to those units. Over on the right side, kelvins cancel kelvins, moles cancel moles, and we end up with atmosphere times liters equals liters times atmospheres. The units are strange on the ideal gas constant so that the units work out in the equation. And instead of creating a new unit, they just use this combination of these four units. What the units on the gas constant tell us are the units that we need to use when we use this equation. When we did, I always forget, I think it's Boyle's law is pressure and volume. It didn't matter if the volume was in liters or milliliters, if the pressure was in atmosphere or torr or pascals or something else. As long as P1 and P2 had the same units, the units would cancel out. When we use the ideal gas law, though, the units of pressure need to cancel with the pressure unit in the ideal gas constant, and so we have to use these specific units. No, you don't need to know any of the the pressure conversion factors. I'll give those to you. If you memorize 1 atmosphere equals 760 torr, it'll save you time, because we use that one a lot. So R here is a constant. What does constant mean? Always the same. It doesn't change. Okay? So we're going to see R pop up now in these equations, and what's typical is students like, where's the R come from? What's R? They didn't give me R in the problem. So this is a new thing, and you have to remember it. R is this just particular number. A little bit like Avogadro's number. It's just this constant. I will give this to you on the useful equations sheet for the exam. But you need to remember, oh, R is the constant. I need to go look up what that number is. Okay? And I'll give you this equation too. In higher level classes, they make you memorize it. And one way students remember it is they say PIV NERT. So you'll hear me sometimes refer to this as PIV NERT. It's the ideal gas law. So we can use the ideal gas law to solve problems where conditions are not changing. So let's look at this example. An automobile tire at 23 degrees Celsius with an internal volume of 25.0 liters is filled with air to a total pressure of 3.18 atmospheres. Determine the number of moles of air in the tire. So we've been adding new equations as we go along. And one of the things that's challenging in chemistry is to take these word problems and translate them into mathematical equations, right? And you look at this question and you're like, I'm not sure what to do. We can apply the same strategy we did for the other gas laws of making a table, pulling the numbers out and seeing what numbers we have, and that'll help us to know what do we do with those silly numbers. So we'll just start out like we did with all the other gas laws, forgetting to enter drawing mode. One of these years I'll remember that. Wait, I haven't even been doing that for a year, so anyway. We'll make a table, just like we did before. So we come across the first number, 23 degrees Celsius. Degrees Celsius measures temperature. So this is our T column. What is wrong with this temperature? It needs to be in Kelvin. So we're going to take 23 degrees. I'll do it down here because I want to save some room in the table. 23 degrees, and we're going to add 273, and we're going to get 296. So I'm going to write that in here, 296 Kelvin. Just change to Kelvin right away. We go on, the next number is 25.0 liters. And it says volume of, so that's a good clue that this is our volume column. Filled with air to a total pressure of, here's the next number, 3.18 atmospheres. It's really, really important to write the units. Okay, write the units down. What should I label this column? P, because this is the pressure. There aren't any more numbers in that problem, are there? What do we do with this second row? Well, it turns out we don't need it. We didn't necessarily recognize that when we started looking at the problem. Now that we've pulled all the numbers out, we see that we don't have a situation 1 and a situation 2. All the problems we've done so far with Boyle's law and Avogadro's law, there's been an N1 and an N2, right? This time there isn't. Okay, so we drew something in our table that we didn't need. That's okay. We're just going to erase that. So we'll just erase what we didn't need. And now we look at what we've got here. We've got temperature, volume, and pressure. And what are they asking us to find? The number of moles. And the letter for that is N. So N equals question mark. So then we go to our cheat sheet with all the gas equations on it. And what we're going to do is we're going to look for an equation that has these letters in it, T, V, P, N, without any subscripts. And the one you'll find is Pivnert, PV equals nRT. We know what pressure is, we know what volume is, we know what the temperature is. They're asking us what N is, and what's R? Yeah, it's that gas constant. I'll write it up here. 0.08206. That's not a 6. Liter atmospheres per mole Kelvin. So here's our equation, and we need to solve for N. One of the nice things about Pivnert is it doesn't have any fractions in it. So we don't have to cross multiply or anything. We can just rearrange it. So how do we get n by itself? Divide by RT. The things that we want to get rid of, R cancels R, T cancels T. If we do that to one side, we have to do it to the other side. I'm going to erase our little scribblings down here because I need the space. So now we have n equals PV over RT. Check the units on R and make sure that your temperature, volume, and pressure are using these units. That'll save you some time. It's easier to convert the units before you stick it into the equation. And they match up. So we've got temperature in Kelvin, volume in liters, pressure in atmospheres. If they give you the pressure in torr, we've learned how to deal with that. Just convert to atmospheres and put that in your table. If they give you volume in milliliters, convert it to liters. Just get all the units straight and then plug the numbers into the equation. So here's our pressure is 3.18 atmospheres. Our volume is 25 liters. Down in the bottom we have R, 0.08206 liter atmospheres per mole Kelvin. And the temperature, we're going to use the Kelvin temperature, 296 K. Now get out your calculator, because here we have that situation where we're dividing by two numbers. Okay, and there's more than one way to think about that, but you have to figure out how to communicate with your calculator so that you get the correct answer. The way I do it is I multiply by the top, 3.18 times 25. I divide by each thing on the bottom. So I divide by 0.08206, and then I divide by 296. And I'm going to round my answer to 3 sig figs. I'm going to get 3.27. What unit is on that answer? Moles. So the number of moles in that tire is 3.27. Did you get the correct number on your calculator? The common mistake would be to accidentally multiply by 296, and then you'll end up with a really big number instead. And that tells you just have a calculator problem, which we can fix. Any questions? Yes. Well, so we're talking about how do we do this on the calculator. There's different ways to think about it. Some students like to take the top two numbers and multiply them and write the answer down. And then they multiply the bottom numbers and they write it down. And then they take the top and divide by the bottom. That works. It's more work. And my philosophy is every time you have to write something down and punch numbers into your calculator, you have an opportunity to make a silly mistake. So I prefer to avoid things like that. Another way to do this is to take, here I'll use red, to take the 3.18 times the 25, and then you hit, I guess I'll put it over here, divide, and to use parentheses on your calculator times close parentheses, and that will work also. The idea of dividing by 296 really bothers some students. And, we just all think of things in different ways, and that's fine. There's not one perfect way that's good for everybody. Yeah, it's a little less confusing for him to combine them. So that's fine. I'm going to show you the way I do it, but you come up with a way that gets you the correct answer with your calculator. That's the important thing. Okay, I try to be consistent because I don't want to confuse people. Your question?
Yeah, in the answer says moles, just because
How do the units work out?
uh-huh.
Okay, so let's look at that because that's a good question. These units are messy because we have a fraction within a fraction. So over here, what we've got going on with just the units is we have atmospheres times liters on top. And on the bottom we have liter atmospheres per mole Kelvin times Kelvin. So when you have, I forget the math term for this, a fraction and a fraction is what I think of it as. To bring this, to get rid of this guy, what you're going to do is you're going to flip him upside down. And so this is the same as mole Kelvin per liter atmospheres times the rest of it, atmosphere liters per Kelvin. So this fraction in the denominator, to get him out of there, I turn him upside down. So I put mole Kelvin on top, I put the liter atmospheres on the bottom, and then I bring him out. So now liters atmospheres cancel, liters cancel, kelvins cancel, and we see that we're left with moles in the numerator. Inquiring minds want to know how that works out, so that's how it works out. If you don't care how it works out, then ignore that part. If you've got your units, if you're using liters, atmospheres, moles, and kelvins, the numbers will work out, the units will work out, and you can just look at N and say, oh, that should have units of moles, slap moles on the end. Good enough. Yeah. Any other questions? You guys are asking good questions today. Let's do another example. What is the pressure in a 304.0 liter tank that contains 5.670 kilograms of helium at 25 degrees Celsius? So let's just follow that approach. Oh, I guess we're in red now. Okay, fine. Of using a table. Just start a table and write stuff down and see what happens. First number, 304.0 liters. Liters measures what? Volume. And so we're going to label that column V. V for volume because liter measures volume. And then it says 5.670 kilograms of helium. Does that match up with anything in our gas laws? We're going to need to convert kilograms to moles. This is related to N, but N is in moles. N is number of moles. So we're going to get N from this, but it isn't N yet. So maybe we'll label this N, maybe. And then the next number is 25.0 degrees Celsius. That's a temperature, right? So we'll put a T here. And what do we have to do to temperatures? Change to Kelvin. So 273 plus 25 is 298 Kelvin. And again, it turns out we didn't need the second row. It's fine. I'll just go and erase it. So then we say, well, what are they asking us to find? What is the pressure? So we're looking for P. This is what we're trying to find. So what equation do we need to use? PV equals nRT. So we're going to use PV equals nRT. How do we know that? Well, we have one volume. We have a thing that's related to N, and we know we could get N from it. We have T, and they're asking us for P. None of the other equations match up with this. So Pivner it is. We're solving for pressure this time. So to get pressure by himself, we need to divide by volume. So volumes cancel out. We do it to the left side, we have to do it to the right side. So now our equation is pressure equals number of moles times R times the temperature divided by the volume. Excuse me. And we remember that R, or we look it up, 0.08206, and those crazy units, liters, atmospheres, per mole, Kelvin. The units on R tell us what these other units have to be. Liters is good, kilograms is not going to work. Kelvin is fine. So we need to fix this. We need to change kilograms to what? First to grams, and then to moles. So we're going to do kilograms to grams to moles. Because that is the amount of gas. They gave us a mass. We need a number of particles. We need moles. So grams to moles, we've done a lot of that. That's the molar mass. They tell us here it's helium. What's the molar mass of helium? 4.00. I'll round that to 4 sig figs from that table. 4.003 grams of helium equals 1 mole of helium. We got that from the periodic table. What's the relationship between kilograms and grams? 1,000. Kilo means 1,000, right? 10 to the third. So we've got kilo here. I'm going to write what it means over here. 1,000 or 10 to the third. So there's our conversion factors. What happened in there? So I'll just throw this in here, 5.670 kilograms. And here's dimensional analysis coming back at us again. I'm going, our path was kilograms to grams to moles. So I have kilograms to grams to moles. Remember that? Kilograms to grams to moles. It's like Dora trying to find the snowy mountains. Kilograms to grams to moles. The previous unit is what we divide by because we want those extra units to cancel out and get out of there. Gram goes down here. We get all the units in. We wrote our conversion factors up here, which you don't necessarily have to do. You can pull them out of your head, but sometimes it helps to have them written down. So here we have 4.003 grams per mole. So that's going to go over here. It was 1 mole and 4.003 grams. And then for the kilograms to grams relationship, it was 1 kilogram and 1,000 grams. So we do the math, we get 5.67 times 1 times 10 to the third divided by 4.003. That number should have 4 significant figures. 1416. I'm going to just throw in an extra one and the units on that will be moles. It's kind of off the screen, sorry about that. So that is N. So I'm going to write that in here. You don't have to do this, but 16.4 moles. Now we have N with the correct unit. We've got the correct units on all of our quantities, so now we're ready to put these numbers into the equation. So 1416.4 moles times R, 0.08206 liter atmospheres per mole Kelvin, times the temperature, 298 Kelvin, and divided by the volume, 304.0 liters. .08206 times 298 divided by 304. 113.9, and what unit will that have? ATM. Doing the unit canceling is kind of confusing, but we had all of our other terms with the correct units, and so then pressure will end up being the pressure unit from the constant. Anybody else come up with that number, 113? Okay. Always a good idea to do these calculations twice. Any questions? This problem is a little more difficult because you can't just take the numbers as given and put them into the equation. You have to do some converting of units first. So here's another gas law problem. At what temperature in Celsius does 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.40 atmospheres? There's like an infinite number of problems that can be asked about the gas laws. Well, let's follow our same approach and make a table. One and two, just because you never know. So the first number, 121 milliliters. Milliliters measures what? Volume. So I'll call that the V column. 27 degrees Celsius. What should I label that column? T. What do we have to do to the temperature? Change it to Kelvin, right? Always have to change Celsius to Kelvin. So 273 plus 27, I think, ends up being 300, right? .05 atmospheres is the next number. How do I label that column? P for pressure. Next number, 293 milliliters. That's the same unit as one of the other ones. So I don't want to put this in a new column. In my columns, I'm matching up quantities and units. 293 milliliters is a volume, so I want to put that in the volume column. So I'm going to have 293 milliliters over here. And then 1.40 atmospheres, that's another pressure, so I'll put that one in the pressure column. a little bit like sorting things, like sorting silverware, and you've got knives and forks and spoons. And so don't put each piece of silverware in a separate container. Let's put all the forks together and all the spoons together, okay? So here we've got our forks, and there's our spoons, and apparently we're missing a knife. We ran out of numbers, and that time it turned out we did need the second column. So I'm just going to erase the extra lines I drew there. We've got a blank in our column, and we also have to ask, what's the question? What temperature? Well, in this blank, we should call that T2. That's a temperature, and so that tells us we need to solve for T2. We need an equation that has volume 1 and 2, temperature 1 and 2, pressure 1 and 2. Have we seen one of those yet? Not quite. We've seen combinations. We've seen parts. We've seen volume and pressure. We've seen temperature and pressure. What do we do? There's another one that your book doesn't specifically come out and tell you about. So I'm going to show you how this, works out, just for those of you who are mathematically a little more curious. So we'll take PV equals nRT, ideal gas law, right? And so that's true, and we'll give these subscripts. I'm not going to give R a subscript because it never changes. So under one set of conditions, the pressure and the volume multiplied equals the moles times the gas constant times temperature for this gas. That's also true under other conditions, such as P2, V2, N2, R is always constant, and T2. What if I take one pivnert and divide it by another pivnert? So if I divide one side of an equation by something, I'm supposed to divide the other side by the same thing, right? nRT doesn't look like PV, but does N2R T2 equal P2 V2? It does. So I am dividing by the same quantity. Okay, so I made a big mess. What's R over R? 1. Those R's cancel out. Now, essentially, I have created an equation that relates all 4 variables. And what I can do is I can cancel out whatever I don't need. What's not changing in this problem? The pressure's changing, right? We've got 2 pressures. Is the volume changing? Yeah. Is the temperature changing? Well, we think it probably is. What about N? It doesn't say anything about N. So then we are left to assume that N is not changing. That it's this particular gas sample, and we're just messing with it. We're not actually adding or taking out any of the gas. So in this example, N is constant. So I'm just going to use my eraser to clean that up, because I can. This is one form of what's called the combined gas law. And I will give you this gas law. The way that it's usually expressed is P1 V1 over T1 equals P2 V2 over T2. So I will give you that, and you may need to use that doing homework. That's called the combined gas law, because it combines 3 of the gas laws. So you'll have that available on your extra sheet of information for an exam. So then when you end up with a question like this and you see that you need V with 1s and 2s and T with 1s and 2s and P with 1s and 2s, you go look and you see that and you're like, oh, there, that's the guy I need. Unfortunately, this has fractions in it, so we're going to have to rearrange that. What are we solving for? We're solving for T2, this guy down here on the bottom. But the first thing we need to do is cross multiply to get rid of the fractions, because those tend to mess us up. So when we cross multiply, we get P1 V1 times T2 equals T1 P2 V2. And again, there's other ways to approach this. This is just the way that makes sense for most of the students who are taking this class. So if you have a better way, you go ahead and do it. Here's T2. So now I need to rearrange and get T2 by himself. And I do that by dividing by his friends. So P1 cancels, V1 cancels. If I do something to one side, I have to do the same thing to the other side. And now I've got my equation. So temperature 2 is temperature 1 times pressure 2 times volume 2 divided by pressure 1 times volume 1. R isn't in this one, is it? It's not. So we don't have to use the units of R. We always have to use kelvins for temperature, even though it's asking us what's the temperature in degrees Celsius. You still have to use kelvins. I can prove it to you mathematically, or just believe me, okay? It's true. What about these other units? The one thing we want to look for is that our volume 1 and volume 2 have the same units. Here they're both milliliters. We don't have to convert them to liters. You can if you like to do that, but you don't have to. In our equation, the volumes divide, and so these milliliter units are going to cancel each other out. Our pressures just need to have the same unit. We've got atmospheres and atmospheres, we're good. If one of these, if this first one was in torr, then we'd have a problem. And we need to convert one pressure unit so that they're both the same. So it can save you a little grief to just check your units. So let's now plug them into our equation. Temperature 1 include the units 300 Kelvin. Pressure 2, take your time and make sure you're grabbing the right numbers. Volume 2, 293 milliliters. And in the bottom we've got pressure 1 and volume 1. And let's double check our units. Atmospheres over atmospheres, milliliters over milliliters. We're left with Kelvin, which is a unit of temperature. It's a good sign. Again, we've got two numbers in the denominator, so be careful. I've got 300 times 1.40 times 293 divided by 1.05 divided by 121. And this comes out to 969. Kelvin. Anybody else get that number? I rounded it to 3 sig figs. Okay. Is that the answer? Not quite. Ask for temperature in Celsius. We need to convert to Celsius. We do that by subtracting 273. And there's our answer. Does anybody else think those numbers are kind of cool? You got 969 Kelvin, and you end up with 696 Celsius. The 6's and the 9's switched places. It's like they just flipped upside down. I wonder if the author did that on purpose, just because it's cool. I don't know. I see things like that in numbers. Like the last 4 digits of our phone number are the years that my husband and I graduated from high school. How random and crazy is that? Our phone number, the last 4 digits, which in Readly, that's pretty much all you need to know. The last 4 digits, the first 2 are the year I graduated from high school, and the second 2 are the year my husband graduated from high school. That's just fun. That was fun. Interesting. And then that doesn't tell you what my phone number is, does it? Not that it would do you any good, because a child would answer it. Because that's basically the kid's phone, the landline. Any questions about this problem?